All right, today we're going to go on a bit of a journey. We're starting with something as simple as a switch, and we're going to end up with circuits that can generate complex signals all by themselves. We're going to explore the absolute fundamental building blocks that make all of modern electronics, especially in a field like biomedical engineering, not just possible, but incredibly powerful.
So, how in the world do you make that leap, right? How does a bunch of simple parts on a circuit board somehow learn to create something as vital as a signal for a pacemaker or filter out the noise from a faint ECG reading? Well, that's the big question we're going to answer today by stacking up our building blocks one concept at a time. Okay, let's start at the very beginning with the absolute cornerstone of all modern electronics. This one little device, invented way back in 1947, is basically the microscopic heart of every single gadget you own. I'm talking, of course, about the transistor. At its core, a transistor really has two main jobs. It can act like a ridiculously fast electronic switch, turning on and off millions of times a second. Or it can be an amplifier, taking a tiny, weak signal and making it much, much bigger. This dual personality is what makes it so incredibly useful. To really get how they work, think of them like valves on a water pipe. The one on the left, the BJT, is like a valve that's controlled by a little trickle of water. A small current opens up the main valve and lets a much bigger flow of current rush through. Now the one on the right, the FET, is totally different. It's controlled by pressure, or voltage. You apply a voltage to its gate and it opens the channel without really needing any current to flow into the controller itself. And that difference is absolutely crucial when you're deciding which tool to use for a specific job. So great, we have this amazing little amplifying device. Let's try to build something with it. Making a small signal bigger is one of the most important jobs in electronics, especially when you're trying to capture faint biological signals. But as we're about to see, using a single transistor to do this is surprisingly tricky. Just look at all the parts you need for a standard amplifier circuit. To get that one little transistor there in the middle to do its job properly, you need this whole support network of resistors and capacitors around it. And every single one has to be carefully chosen just to get the transistor into its happy place, a stable operating condition where it can actually amplify. And here's where the real headache begins. That so-called happy place is incredibly sensitive. If the room gets a little warmer, the circuit's behavior just changes. And if you swap out one transistor for another one, even with the exact same part number, its internal specs can be just different enough to throw your entire design out of whack. It is a delicate and, frankly, a very frustrating balancing act. So you see the problem, right? We have this fundamental component, but it's just finicky and difficult to work with. And this difficulty creates a gap, a real need for a better solution. So what if we could take all of that complexity and just package it into a new, much more reliable building block? And that brings us to the hero of our story, the operational amplifier, or as everybody calls it, the op-amp. Now, this isn't just one component. It's an entire, complex amplifier circuit that's been shrunk down onto a tiny little chip. And it was designed specifically to solve all the problems we were just talking about. The secret to the op-amp's power is its absolutely insane open-loop gain. We're talking an amplification factor of over 100,000, sometimes even millions. Now, by itself, that is completely useless. The tiniest bit of noise would just slam the output to its maximum voltage. But this massive gain is the key to everything. So how do you tame a beast like that? You use a really clever technique called negative feedback. All it means is you feed a tiny little bit of the output signal back to the input. And when you do that, something amazing happens. The circuit's performance suddenly doesn't depend on the op-amp's internal chaos anymore. It only depends on the stable, precise components you connect to the outside of it. And this slide just says it all, doesn't it? On the left, there's our messy, sensitive transistor circuit. On the right, the op-amp amplifier. In that circuit, the gain is simply set by the ratio of two resistors. That's it. It's stable, it's predictable, it just works. This is the power of abstraction. We don't have to worry about the messy physics inside the chip anymore. We can just use it like it's a perfect, ideal building block. Okay, so now we have this incredibly powerful and predictable block. What else can we build? Well, it turns out that by just changing the parts you put around it, you can make the op-amp perform all sorts of amazing tasks that go way beyond simple amplification. For example, pop a capacitor into the feedback loop and bam, it's a filter. This active filter can let the slow, important signals from a heartbeat pass right through, while blocking all the high-frequency junk, like noise from muscle tremors or electrical interference. You can see why this is absolutely critical in biomedical devices. Now, what if you swapped that feedback resistor for a capacitor in a different spot? Well, believe it or not, the op-amp is now doing calculus for us. This circuit is called an integrator, and its output is based on the input signal over time. This is a fundamental building block for all sorts of advanced signal processing. Okay, so we've amplified signals, we've filtered them, we've even done math on them, but what about that next step on our journey? What about creating a signal where there was nothing to begin with? This is where we have to flip one of our core ideas completely on its head. See, up until now, we've been using negative feedback to create stability. To create a signal from scratch, we actually need positive feedback. We have to feed the output back in a way that reinforces the input, creating this self-sustaining loop. And that is the core principle behind any oscillator. So how does this seeming magic actually work? Well, it all starts with the tiny, unavoidable electronic noise that's always present in any circuit, just a faint whisper. The op-amp grabs that random whisper and amplifies it like crazy. Then, a special network of resistors and capacitors acts like a filter, only letting one very specific frequency get through. That pure tone gets fed back to the input, gets amplified again, and the cycle repeats, growing stronger and stronger each time until it stabilizes into a perfect continuous wave. And here's a perfect example of a circuit that does exactly that, the Wien Bridge oscillator. It's this really beautiful, elegant design that cleverly uses positive feedback to pick the frequency and get the oscillation going, while also using a little negative feedback to control the gain and keep the final sine wave stable and clean. So let's just step back for a second and look at the toolbox we've just put together. We've gone from the most basic component you can imagine to these sophisticated circuits that can process and even create information all on their own. Our journey started with the transistor, right? The raw material. Then we hit the challenge. It was just too variable and complex. And that's when the op-amp came in as the elegant solution, an abstraction that packed all that difficulty into one reliable building block. And with that single block, a whole new world of signal processing opened up, giving us the power to build some truly incredible things. Which brings us right back to our original question. We now have the tools. We've got amplifiers to read the faintest neural signals, filters to clean up an ECG, and oscillators that can drive a pacemaker. The final question isn't about the components anymore. It's about what we, as innovators and engineers, can imagine and build with them. What life-saving device will you create?